So here's a schematic illustration of what was happening. We see the alpha particles being shot at the gold foil. Gold can be pounded into a foil that's only a few atoms thick, so most of these particles go through without ever touching the nucleus. Notice the nucleus here is drawn to be about 1/5 the size of the overall atom, when in fact it's 100,000th the size of the overall atom, so it's much smaller than this. If an alpha particle happens to get really close to the nucleus, then the nucleus is big and heavy, with nearly 20 times the charge of the alpha particle, 40 times the charge of the alpha particle, and 50 times its mass. So the alpha particle can bounce off of that almost as if the gold particle stayed at rest. We can understand that in more depth and even calculate how close the alpha particle gets to the nucleus if we consider energy considerations. So here we have an alpha particle coming in. It comes in with an energy. The characteristic energy might be 5.3 mega electron volts, or 5.3 million electron volts. The energy an electron would pick up if we accelerated it through a potential difference of 5.3 million volts. That's coming in with a whole lot of energy. It penetrates through the electron cloud, where there are 79 electrons in a gold atom, and comes near the nucleus, which has 79 protons and therefore 79 positive charges. As it gets in close, some of this kinetic energy is converted into potential energy. Eventually, if it's on a dead-on collision course, it'll get to the point that all of that energy is potential energy, and none of it is left in kinetic energy. Then, as it is pushed back, that kinetic energy is that potential energy is retransferred back to the kinetic energy, which shoots the alpha particle back out. Now we could ask, how close does it have to get for all of this energy to be potential energy? Well, we know that the formula for potential energy is K Q1 Q2 over R. And Rutherford knew that the alpha particle had a charge of plus 2e, and the gold nucleus had a charge of plus 79e, all over R. So if I solve that for R has to equal 158 Ke squared divided by the energy. Now we could put in K in SI units and E in SI units and figure this out. But I happen to know that Ke squared is 1.44 mega electron volts times a Fermi, where a Fermi or femtometer is 10 to the negative 15 meters. I can then divide that by the energy we've got, 5.30 MeV, and you will notice the units cancel, and I'm going to get Fermis out. Bringing up a calculator, this is 158 times 1.44 divided by 5.3. So we get within a distance of 43 Fermis, or femtometers, of the nucleus, of the center of the nucleus. Now consider the atom is about an angstrom, or 10 to the 5 Fermis, and this got within 50 Fermis of the nucleus. Obviously, the nucleus must be much smaller than the entire atom.